Okay. I'm gonna open a random document so we can use it. Random document so we can use it. Just a second. Okay. So our Physics 306, the Monday section. By the way, is Jason here? No, not this Jason. I'm talking about the other Jason in Physics 302. All right, forgive me. So the other Physics 306 students, they're done, and let me zoom in a bit. They're actually, hello, Jason. Yeah, some Jason sent me an email. I think it's not you. This Jason, who's this? Bella, it's you. And it says classical physics. You guys, aren't you modern physics class? I'm confused. Isn't Physics 306 right now?
Yes, Dr. Modern Physics.
Okay. And how come you're receiving the emails of another class? Because you replied to the email of the other class. Well, you want to join to listen. Or I did a mistake and confused you. Should Jason, please, I need you to clarify what just happened.
Doctor, he's talking in the chat,
Okay.
and he's saying that he's taking both courses, 302 and 306.
Oh, yes. All right. I'm so sorry for that. Okay. So, yeah. All right. So that's why probably I confused you. Listen, I have 5 sections and every section has a different plan. So it's normal for me to be confused, but I don't want you to be confused. So yeah, anyway, I'm gonna follow my plan and Jason, try to stick to it as much as possible. So for Physics 306, the Monday section, because eventually you're gonna have your midterm with them. And don't feel bad because we have sections on other days as well. They're done with lab 1 and you too, you're done with lab 1. Their lab 1 is corrected. In your case, it's not corrected yet. It's gonna be corrected this week. Last week, they did the theory of lab 2 and lab 3, and they did the experiment of one of the labs. All right, so the experiment for one of lab 2 or 3, and it was actually planned that they're gonna have the other one this week, but they couldn't. That's why yesterday they had a week off. I only had meetings with them on one-to-one for the students who had questions. Since you are a bit behind, I cannot give you a week off. I would love to. I thought if we cover the theory of lab 2 and 3, and next week I see you, we do the experiments both for lab 2 and 3, we could cover the whole thing clearly. If we finish the theory of lab 2 and 3, next week it's not gonna be long since you can start immediately with the experiments. All I have to do is pass through the benches to make sure everybody is working fast and the procedure is well connected and so on. All right, which means your plan would be the following for today. Cover lab 2 and 3 theory only, okay? And it shouldn't be difficult since we're covering something that you already did in high school. Fine?
Doctor?
Yes?
So we don't have to submit a lab report?
So you will have a week off from lab reports. However, for next week, you're going to have 2 lab reports, but maybe I can extend it more than 7 days. Let's say around 10 days. Please. Yeah. And we're
maybe 10 days.
Yeah, we're going to talk about this ayah. Remind me next week. So let's take it 1 week at a time. And again, I'm here to help you. I'm not here to confuse you, neither to make you frustrating, okay? So as long as you understand what you're doing, that's the purpose. As you can see in my plan, back on Blackboard, I said I want to cover again, continue the part of graph skills. We can put it on hold. I believe this is more important for the moment. All right, so yes, so I'm gonna provide you with presentations for lab 2 and 3 for this one, and probably a video of the procedure for you to keep. You don't really need it because I'm gonna do the procedure on your bench next week, but keep the video just in case you would want to see it before coming to the lab next week. Okay, so our first presentation is gonna be lab 2. I'm gonna save the edits and send it to you. Okay, so let's get ready. I'm gonna put the list of participants in here. just for me to be able to follow up on who's with us. All right, let me make this a bit smaller. I want to make this a bit smaller to be able to see the whole thing. Okay, I can move this to the side, move this to the side. Okay, it's okay, Muhammad, I'm glad you're here. Okay. All right, fine, I'm ready. So experiment 2 is a little bit heavy in data analysis. Okay, so you're gonna be upset and it's a long lab report, but remember it's your only lab report that is gonna be this long and this tough, which means it's a good practice for you before the midterm. So I know you're gonna be eventually 3 in a group, not 4, you're gonna be 3, and probably you can divide the work, but make sure you know how to do the whole thing yourself, okay? So lab 2, capacitance and dielectrics, we're still under electrostatics, no currents involved yet. We have 4 sections in this lab. So part 1, 2, 3, and 4. And this is how the lab report looks like. The first part, you're gonna deal with the capacitance of a capacitor. You will be given 2 plates facing each other. I'm gonna show you. Part 2, you're gonna insert a dielectric material between the plates. Part 3 is something else. You're gonna be given a box of capacitors. Your job is to connect them in series and in parallel. Many of you will be happy with this part because you're gonna create a circuit. I know we don't have a power supply yet, so no current flow, but capacitors in series, you're gonna find the C equivalent of them by simple measurement. And eventually you will be given a coaxial cables, and what are they? You're gonna see in a bit. So 4 parts. I'm gonna start with part 1. This is exactly what you have. I'm gonna zoom in. You have 2 plates. Now you tell me, what is the area of 1 plate? How do you measure it? Or how do you calculate it? Look at the plates. Are they squares or discs?
Is it?
Yes. So Mustafa just wrote pi r squared and it's a disc, Dua as well. So you have 2 discs facing each other. You just need to do pi r squared for each. How do you measure r? How? Which measuring tool I mean? Yes, just unmute and talk. Let's do it quick. So measuring tools to measure r. I don't see an answer yet. It's gonna be a regular ruler. However, if you really think about it, you're measuring diameter and not the r. And now that you measure the diameter, the uncertainty is gonna be the smallest subdivision divided by 2. Think about it, and eventually you're gonna find the error on the area. How do you do that? Probably you know, probably you don't. Go back to me if you need help. You're gonna do the propagation of error. So area of the plates you can measure easily. Distance between the plates. So to find the capacitance of a parallel plate capacitor, you use epsilon 0 A over D. A is the common area of the plates, which is pi r squared. D is the distance between the plates. And if I grab a pen, it's gonna be this distance. Make sure you measure from the inside, also using a regular ruler. And how would you calculate the capacitance? You can if you want, but if you need to measure it, you will be given an LCR meter. An LCR meter is a digital measuring tool. So it has 2 terminals. You will end up with 2 cables. 1 cable will be connected to 1 plate. Actually, to be honest, it will be connected to this item. You see, there's like a knob going out of your plate and another knob going out of this one. And you're gonna see on the screen a digital measurement of the capacitance. It's gonna be in picofarad. Can you remind me, picofarad is how much? The order of magnitude. 1 picofarad is how many farad? Pico?
Times 10 to the power minus 12.
Yeah, can you imagine how small it is? So nano is -9 and pico is -12. This is a very small capacitance. I know the capacitor is huge, but we don't care about the size. All right. And as the distance goes to 0, the capacitance is going to increase a lot, but it's going to stay in the picofarad. All right. So this measuring tool is very precise. I cannot use a regular multimeter for this one due to the fact that you need to go down to the picofarad. A regular multimeter would go down to nanofarad, but not picofarad, okay? Now you have a problem. Since the capacitance is very small, those wires, if you just disconnect them from your capacitor, they're gonna measure something farad, and it's gonna be around, I don't know, a few picofarads, 3, 6 picofarad. To be honest, I cannot remember. So you're supposed to disconnect from your capacitor, measure the capacitance of the wires, and then minus the answers from all the results, okay? Now I'm gonna insert a text box to write a bit what we're gonna vary, what is constant, and what is the measurement, okay? So we're gonna keep, yes, I'm gonna repeat a bit, Rita, what we're gonna do. The constant here in this experiment is gonna be the area. The area of the plate is not gonna change. Now the variables. I think there's only one variable, it's the distance, small d. So we're gonna take 5 millimeters distance between the plate, then 10, then 15, then 20, then 25, and so on. And we're gonna measure one thing, it's gonna be C. And we're gonna have a plot that is linear. Now my question for you, probably for Karen, if you want Karen to try. Karen, if I need to plot something, what will you plot looking at your variable and your measured value? What will you plot to get a linear relationship? Can I plot C versus D, for instance? Since D is the variable and C is the measured value, I don't see why not. But C versus D will give you a linear relationship, yes or not? So the equation is, I'm gonna write it again, it's epsilon 0A divided by D. Does this give you a linear relationship? You can write it down as epsilon 0A multiplied by 1 over D. So if you plot C versus D, do you get? So you'd rather plot C versus 1 over D. Here you have to be careful. D is in millimeters. So 1 over D is going to have a creepy unit. So just make sure you don't do mistakes over the unit. Some of the students in my Monday section, they were struggling a bit with the picofarad and millimeter to the -1. But eventually everybody got a straight line passing through the origin. Question number 1, and let me insert a text box here just to tell you what to expect. They want you to plot, and this is easy, you know how to plot. 2 linear regression, find the slope. This is also, I believe, easy. Question number 2, 3, they want the error on the slope. Do you feel ready to find the error on the slope? Using the Linus method or any method of your choice.
Yes, Dr. On Excel.
All right, Linus. And then 4, they want you to say, to know what does the slope represent? What do you think? I'm trying to answer some of the questions to help you for next week's lab. What does the slope represent? If you look at the equation very well, you're plotting C versus 1 over D. What would be? It's gonna be epsilon 0 times A. So exactly. So they will ask you to deduce epsilon 0. So question 5, deduce epsilon 0. Deduce epsilon 0. And this is easy. And then they want the error on epsilon 0. Error on epsilon 0. And how would you do that? If you have the error on the slope and you found epsilon 0 from the slope, you need to find a way to find the error on epsilon 0. Now the question is, epsilon 0 by definition, like the theoretical value of epsilon 0, how much is it equal to? You should know it from the course. Probably you remember, probably not.
Yes, doctor, they told us not to memorize it because it will be given.
Okay, so it's gonna be 8.85 times 10 to the -12. The 4 pi times 10 to the -7 is the magnetic property, not the electric. So the magnetic permittivity, and you're gonna use it with SI units. We got a lot of groups, like all the benches, they got this value. For the students who did not get this value, usually they did some mistakes. For instance, to measure the radius, they measured the diameter and they assumed this is the value of the radius. Like tiny mistakes, it happens. Some students had issues with the 10 to the power, like the order of magnitude. It was a mix of the units they had and some mistakes they did. Some of the students used SI unit in the graph directly. So farad and meters. And you know, if C is in farad, it's going to be a very small value. And here Excel would round your values. So don't give Excel very small values. You'd rather keep your values in picofarad for Excel to make sense out of those significant figures. Otherwise, any small value will be assumed to be 0. Don't do that, okay? However, I noticed in the Linus, even if Excel tells you your slope up to 1/6 fig, when you do the Linus, it gives you more significant figures. Anyway, we're going to play around with the data, and this part is going to take you some time, but it's really important to do it. Like, it's an excellent practice. Part 2 is super fast. Part 2, you're going to take your capacitor. Let's say that these are the plates. You're going to insert a dielectric. You will be given plastic and cardboard, okay? A regular plastic material and cardboard, okay? And I know that plastic and cardboard are not super informative. Like plastic, you have 10,000 types of plastic, and cardboard as well. Eventually, you're gonna find K, the dielectric constant of cardboard and plastic. But if you're gonna go online to see, you will find so many different types of plastic, which is okay. So you're gonna take your plastic material, you're gonna insert it inside the capacitor, and you're gonna close on it. So the distance between the plates that I'm gonna call small d is gonna be equal to the thickness of the dielectric. Something like 1 millimeters or 1.5 millimeters measured with a regular ruler, that's not very precise. I don't like this. I'd rather have a micrometer to measure this very small thickness. But make sure there's no air in between. Close just enough and don't squeeze a lot on the dielectric, because you're gonna measure C with the dielectric and C without the dielectric. So I'm gonna call this C0 without the dielectric, and this is CD with the dielectric. I want D to remain the same. So make sure not to squeeze a lot, because if you remove the dielectric, D is gonna change. The area is constant, obviously. How do you find K? So this is measured and this is measured. A and D constant. How do you find K? So you measure with, without. The experiment is done. Very simple, very quick. How do you find K?
What is K?
K is the dielectric constant. So the C equals epsilon 0 over A, epsilon 0 A over D, is the capacitance in case you have vacuum between the plates. I'm gonna call it C0. Vacuum or air. We're assuming it's vacuum, however, it's air. It could be humid, so this is one source of error. If you insert a dielectric, which is an insulator between the plates, and this insulator is gonna get polarized, it's gonna increase the capacitance of your capacitor. Okay, so the new equation in case you have a dielectric will be equal to kappa or K times epsilon 0 A over D. Okay, so the capacitance of your capacitor is going to increase a bit due to the fact that you inserted a dielectric. Fine. Kappa should have a value between 1 and, I don't know, probably it can go up to 7. Some dielectric would give you 5. In your case, you're going to have 1.2, 1.4. I can't remember, 1.6, probably 2.5. So kappa is a value greater than 1 because obviously your capacitance is going to increase. So if it's equal to 2, your capacitance is going to double. So now back to you. If I measure C with the dielectric and C0 without the dielectric, how do I find kappa? Isn't it simply the ratio between the two values? Can you see it? Yes, exactly. So by simply doing CD divided by CO, you're going to obviously find kappa. All right? Have a look again at it. Now C is measured using a digital measuring tool, and this is the digital measuring tool I'm talking about. You can see it on the screen. So what is the error on the measured value? Can you give me a hint? What is the error on the measured value of capacitance if I'm using a digital measuring tool? How would you find the error on the measured value? And
equal to the smallest unit of measurement.
Thank you so much. So we don't divide by 2. Okay, it's a digital measuring tool. we will simply write everything on the screen. So, and the error would be exactly like, who was talking to me again?
Me, Dr. Asif Ismail.
Okay, Qasim. All right, so Asim said, just take the smallest unit. So if it's 0.01, you say, if that, like you have two decimals, you say 0.01, and the unit is displayed on the screen, by the way. It's gonna tell you pico or micro. So now that you know the uncertainty on C, yes, Dua, if it's analog, you divide by 2. Now that you know the uncertainty on CD and the uncertainty on CO, how do you find the uncertainty on K? This is all practice for you. In lab 1, you didn't have all this to practice. In lab 3, you barely have some. So to find the error on K, what do you do?
Propagation of error.
Yeah, and probably we can do it together. Let me go back to the slide. So to find the error on K, Asim, can you help me? Let's do propagation of error. We'll probably give you time to do it on your own. It's basically like A over B. So I'm gonna do the derivative of K with respect to CD, right? You wanna try it? Times alpha CD, all of it squared, okay? Plus derivative of K with respect to CO, alpha CO, all of it squared, and then you do the square root. Let me change the color of my pen. Now, what is this derivative? The derivative of K with respect to CD, anyone? So CD is your X, and you're doing X over constant. It's gonna be 1 over constant, so 1 over C0. And here, C0 is your X, your variable, so it's gonna be constant over X. What would be the value? And please, I advise you to write a lot in the chat, even if your answers are wrong. So if I have constant over X, exactly, Dua, if I were you, I would add a minus. That is not important here because it's gonna be squared eventually. So I'm gonna say negative CD over CO, and the CO is gonna be squared, okay? Anyway, think about it, do the work. Don't forget to round your K to 1 sig fig. No units for K in this case, and make sure K is rounded according to the uncertainty on it. We're done with part 2, okay? Now part 3, I cannot really explain it well because you're gonna do it on your bench. Anyway, you will be offered around 6 capacitance in a box, okay? Yes. I'm gonna remind you Rita in a bit. So you're gonna pick only 3 capacitors randomly from your box. You're gonna measure. The nominal value is what is written on it. The measured value we can measure with a multimeter. I can remember microfarad and nanofarad. So those are much bigger than picofarad. You can use a regular multimeter for those. So you're gonna measure, let's say you pick C1, you write what is written on it. So you write the nominal value, then you measure it and you write the measured value. And you're gonna see the nominal values and the measured values are a bit close, but not too close, okay? And then they're gonna ask you to connect C1 and C2 in series. I'm gonna tell you how to do it later on because if I tell you today, you're gonna forget it. And C1 and C2 and C3 in series and measure the combination. And this is a quick reminder, for a capacitor, a series connection is gonna give you this. I'm sure you remember that. And a parallel connection is gonna give you this. So C equivalent will be the sum of the different C's. And here the inverse of C equivalent will be the sum of the inverse of the different C's, which is for a resistor, it's the opposite. I just gave you the resistor. I thought probably this would help you remember. And remember the capacitance is measured using a digital measuring tool just in case. All right, and then you'll have a table to fill in. Some values are measured, this is measured, and some values are calculated, and different combinations like series, parallel, and different combinations. I think you have around 8 different cases to do. And eventually you're gonna compare calculated and measured by doing the percentage difference. And you're gonna see all the values are gonna be less than 5%, so safe. All right, now I'm gonna open a slide just to talk a bit about the different derivatives. I think this would help you. You need to know the derivative of constant times x. You need to know the derivative of constant times x to the power alpha, power 3, let's say. You need to know the derivative of radical x times constant, derivative of k over x. That's it. Sine, cosine, I think will not be used in this lab. Anyway, if any new derivative will come to us, we can simply write it down again. All right? So how about you talk and tell me the answers for these? Just quickly, it will be a good reminder for some of us. Yes, this is easy. If you have k times x, what would be the derivative? X is obviously the variable. All right, it's equal to k, so this is it. What about the derivative for this one? K is gonna stay, then what? Let's say x to the power 3.
Alpha k x.
All right, but x is gonna be to the power alpha minus 1.
Alpha minus 1, yeah.
Exactly, so I shouldn't write 3, I should write alpha. So it's k alpha x to the power alpha minus 1. Exactly, I'm reading on the chat. If it's 3, it's gonna be k times 3 times x to the power 3 minus 1, which is 2. What about the square root? To be honest, I don't know what it is. I simply do x to the power half. So it's gonna be k times half times x to the power half minus 1, which is gonna be minus half. If I write it again, it's gonna be k divided by 2 radical x. So this is how I do it myself. I'm not a fan of remembering equations. So don't forget the k, Dua. It's gonna be k divided by 2. Okay, so I assume and 2 radical x are both in the denominator. All right, what about this one? We just did it with awesome, I believe. Yes.
This one minus x minus k over x squared.
Okay, so it's gonna be minus k over x squared. I think this is all you need for this lab. And if we need any other derivatives or functions to follow, let me know to remind you. The last part, and I'm happy we're done with the longest lab report ever. Coaxial cables. What are coaxial cables? These are coaxial cables. I'm sure you saw them somewhere around the house. They are 2 cables, but one on the outside and one in the inside. So 2 cables, let's say positive, negative, or blue and red, whatever you want to call them. So this is your first cable copper, and this is a copper mesh. And you have an insulator in between and insulator on the outside. Okay? And this is the capacitance of a capacitor that is cylindrical like this one. C is the capacitance. Really? Why do you get electrified, Muhammad? Those usually take a very low voltage, and usually they're not connected to the mains, which is behind the TV box. Yeah, usually they'll send a signal that is not too high. I'm sorry, it sounds frustrating. All right, so yeah, you know what I'm talking about now, since you will never ever forget them now. So C is the capacitance of those wires, and L is the length. So you're supposed to take the long cable, put it on the floor or on your bench and measure the length. It's gonna be around 1 meter or so. B over A will be given to you, I think, in the manual. And kappa is the dielectric constant of this insulator. All right, and you need to find kappa eventually in the last question. Now, how do you find C? This is, we're gonna go back to our RCL meter. So to measure C, because I believe the values are gonna be small again. So a regular multimeter will not be enough. So you see that this cannot go into the terminals of your digital measuring tool. So Ms. Jinan is gonna give you an adapter that looks like a fork. And then you're gonna connect the fork to the cable, and the cable is gonna be spread on the desk as long as possible. You don't want to turn it and twist it. Okay, so you measure the capacitance. Remember, it's 2 cables, one outside, one inside, and you're connecting both. and you're measuring the capacitance between the two cables, between the plates. Those cables are parallel eventually, right? So you're gonna have a value, then you're gonna remove the cable and measure the adapter alone to minus it from your answer. And then you're gonna do cable 2, and then you're gonna connect. So this is another adapter that Ms. Jinan is gonna give you, and you're gonna connect two cables like this. And you're gonna measure this alone and this alone to minus it from your final result, and C equivalent for the whole thing. C equivalent will be the sum or the sum of the inverse. I don't know, check it out, because eventually they're gonna ask you, is this a series connection or a parallel connection? Probably you're gonna think this is series, and the answer will prove you wrong. And probably you're gonna think it's in parallel, and your answer is gonna prove you wrong. So you do the calculation, you do the measurement, and you compare your answers. And at the last question would be find K. And they will tell you, now that you know K, can you guess what is the insulator or the dielectric? You're gonna go online and check what type of insulator could be in the coaxial cable. What type of insulator has a kappa close to this value? I know this is an open answer and it's gonna be hypothetical. Your answer will be hypothetical. You're gonna say probably this is the insulator, probably not. To be honest, I don't mind whatever your answer is, as long as you evaluate your answer to make sure it makes sense. This is what matters, okay? You're gonna email me a lot in the coming weeks saying we cannot find this dielectric constant. We don't know what the material is. It doesn't matter. Just try to find out and try to say a maybe answer, okay? And that's it. I remember back in the days when we did this lab, the students had difficulties to plot, do linear regression, find the slope, find the error on the slope. I gave them those values to practice, okay? I'm not gonna give you extra work because we still need to cover lab 3. That is really tiny and easy. But if you want, you can simply try this and ask me wherever you're stuck. Plot C versus 1 over D, obviously easy. Do linear regression to find the slope, find the error on the slope, okay? So I'm gonna keep this slide undone unless you want to do it to ask more questions or to make sure you're safe. I'm gonna save the edits and move to our new slide unless you have a new presentation, unless you have questions and you want me to stop for a bit. You're fine?
Doctor, if you have questions, can you request like a one-on-one meeting or something?
Of course, you can request a one-to-one meeting anytime you want, any week you want, and any day you want, and in the evening or in the afternoon, it doesn't matter, okay? Don't wait for a week to be exceptional for a meeting. We can have meetings anytime. Just let me know, and we can schedule the time that is good for you, okay? All right, now I'm gonna check the next presentation. And the title will obviously make you breathe a bit. Resistance, resistivity, Ohm's law. How easy is this? What's that? Grade 9 level? Right, it is grade 9 level. All right, so let's start and let's make it quick. First, George Ohm, the guy who played around with resistors. The outline, we're gonna discuss Ohm's law. Then the experimental board, how it looks like, because I want you to make sense of what I'm talking about. Then they're gonna ask you to measure the resistance. I'm gonna show you how. This is going to be done through Data Studio, and this is your first time doing Data Studio since Physics 302, if you ever did Physics 302, okay? But Data Studio is not gonna be frustrating. It's gonna give you, it's gonna do all the work for you. You just have to know where to start, where to stop, and what to read. Then, and this is a very interesting extension, we're gonna experiment on a light bulb. And the light bulb could be an ohmic device or not an ohmic device, like acting like a resistor or not. I don't know. It's gonna give you a weird behavior and you're gonna raise very big questions about the light bulb. And probably send you the video of the experiment, but in slide number 5 or in the 5th steps, I only showed some screenshots, okay? You can watch the video later to see how things would be. All right, let us start with Ohm's law. You tell me, what is it? What do you remember? What does it say?
Voltage U equal RI, resistance times current.
Okay, the voltage that I'm gonna call delta V because I'm gonna keep V for potential. And now you're expert knowing the difference between potential and potential difference is equal to RI. If delta V is creepy for you, because personally I don't like it, let's say U equals RI. But again, awesome, U equals RI, what does it tell me? It tells me so many things, and probably we can type them in here. What does it say? One, what does it say? U equals RI. What does it infer?
That I remember that but I remember that resistance stays constant, like U over I always gives the same result, which is R, without a constant resistance.
Okay, resistance is constant is a very important statement, okay? Because for a device to be ohmic, so I'm trying to list the different conditions for a device to be ohmic. It has to follow Ohm's law, but not any random Ohm's law. It has to, the resistance has to be constant. Now I can read that Dua is saying voltage and current have a linear relationship. What she means is they are proportional. So U and I are proportional. And probably I can add, this is not a third condition, it's the same as condition number 2 written differently. U versus I will show a straight line passing through O. And any device that will not give you one of these is not ohmic. All the devices have resistance in them. Any receiver has a resistor, the TV, the fan, I don't know, the coffee machine, and you can find the resistance by doing delta V over I. However, if the resistance is not constant, it's not ohmic. Yes, Reem, what's wrong? You want to eat? Okay, can we eat later? Thank you. Okay. You want to say hi to Reem? Reem, you want to say hi to the class?
Yes.
Reem wants to say hi. By the way, Reem cannot go to school, exactly like me. And this is Reem. By the way, Reem loves sciences and math. And she loves reading, but not too much. She has a book to read now, but she's taking a break. Yalla, Reem, go. Thank you, Reem. All right, so I forgot to tell you that Reem is an excellent athlete. She plays football and she's in the track and field and she competes. Yes, and she's 7 years old. All right, so yes, I'm proud of Reem. That's why I'm talking about her. So we're done with Ohm's law. We're good. Now, what do we have here? Ohm's law quickly, U equals RI with some units, amperes, volts, ohms. And you see here that R is constant and R is not constant, exactly what Asim was talking about. This is ohmic device and this is non-ohmic. All right. Okay, now what do we have? This is a resistor. This is how it's gonna look like. And those are bulbs. Are these ohmic devices or not? Probably sometimes they act like ohmic devices and sometimes they don't. This is the board that will be given. It's provided by Pasco, and obviously this one is gonna be used on Pasco. So let's see what we have. This is a resistance, you see 10 ohms. This is another resistance, 33, and this is 100, it doesn't show. This is the terminals of the 10 ohms, okay? Those two are already connected. So when you see a white line, it means connected. So the white lines are connections, but eventually they're not connected to anything. This is a bulb, we're gonna use it. It says that it takes up to 7.5 volts. This is important in Data Studio. Make sure you don't exceed 7.5, otherwise it's gonna be destroyed and we're gonna change it. If you do by mistake, it's okay. But the voltages we're gonna use are gonna be like 2 volts, 3 volts. Sometimes we go up to 5, but not more than this. Also, I used to tell the students to pick an amplitude that is not too high because you need to look at the bulb to see the behavior. And if it's high, it's gonna give you a discomfort. Personally, I'm very sensitive to light and I would hate to look at a bulb that is very bright, okay? This is a small resistance. It says 1 kilo ohm, could it be? And this is a light emitting diode, like a small lamp. Capacitor, 100 microfarad. another capacitor, 330 microfarad. This is a bulb, not a bulb, a coil. It's like a solenoid. You will see copper wire coiled around it. We're gonna use it many times, this board, so that's why I'm taking time to explain it. And this is an iron core. You can remove it to put it inside the coil to increase the inductance of the coil. I don't know if you remember anything from high school, inductance of the coil. If you put an iron core, it's gonna increase. The unit is Henry. Anyway, if you don't remember, don't worry about it. Now the connections. This is the board. You see, this is a real picture. And this is the science workshop. And these are outputs. It's written here, output. This is another science workshop, and we have both in the lab. It depends which bench you will be on. If you read well on it, it says output, and the output is sinusoidal if you want it to be sinusoidal. Okay, so when you open Data Studio, you will take charge of the generator. You decide if you want sinusoidal or triangular or constant. You decide the frequency and the amplitude. It's lovely. You write down what you want. And you are asked to connect to resistance 1. You take a cable, connect here. Take another cable, connect here. And the experiment is over. That's it. That's it. You go onto Data Studio, you click, record, and stop. The experiment is over. Data Studio will give you voltage versus current. You're gonna do the experiment for resistance 1. Resistance 1 is equal to 10 ohms. Let me write it down so for you to know what we're gonna do. And you're gonna do resistor 2, which is 33 ohms. You will end up with 2 graphs of different slopes, obviously. Voltage versus current, SI units everywhere. For the 10 ohms, they want you to take coordinates of many points. Okay, so you have a smart tool on your screen. You're gonna make sure the smart tool is moving on the straight line, and you write the coordinates here, I and V, I and V. You disconnect resistance 1 and you start with resistance 2, I and V again, I and V again, I and V again. Okay? Then they will ask you to connect them in series, then in parallel. Is that it? So we're done with this table. We should do the series connection, the parallel connection. You may struggle a bit. Let me show you. Probably you can remember this next week. I jumped one slide. Just a second here. Okay, for the series connection, those are already in series. You just have to connect this one and this one. And polarity is not important because it's a sinusoidal voltage, which means it's gonna flip positive, negative. So any polarity is fine. This is the connection of the series connection, that's it. And now for the parallel connection, you need a cable to make them parallel. Then another cable, let me make sure this is small enough. Another cable to connect this from this side and this from this side. So 3 cables in total for the parallel connection. I'm gonna see what you will remember for next week, but again, I can explain it on your bench. They want you to do the calculation and to compare with those. Okay, let me explain. You have I and V, they want you to find R. I and V, find R again. I and V, find R again, and eventually find the average and the root mean square. Many students were upset. They said, "Ma, we already have the graph and the slope is R. Why do they want me to find different coordinates? And then from different coordinates, find R for each, and then do the average and the RMS." They're doing that for 2 reasons. Reason number 1, they want you to see that R is constant. Reason number 2, they want you to practice averages and root mean square, right? And you guys are good with this, so this is really easy. And then they want you to compare the nominal value to whatever value you got in the average. Now tell me again, what do I mean by nominal value? And I'm gonna type the answer here. Nominal value. What is it? What is nominal value? Measured value is what I measure. Calculated value is what I calculate. What is nominal value?
Written on the device.
Exactly. It is the value written on the board. And this value could be right and could be wrong. I don't know. You don't have a measuring tool to measure R directly. You only have Data Studio, so you take it from the graph. So you compare whatever you have in the graph to what's written on it. And your values are will be close. For the 10 ohms, I got something like 9 or 11. So like 10%, this is big. One bench got 12 ohms for 10 ohms. And this is like a lot. So yeah, exactly. Done with part one. Now part two, the bulb. They're gonna give you a bulb. You're gonna do the exact same experiment on the bulb. However, they want you to do two frequencies, and I will write it in here. Frequency one will be below 1 hertz. So 1 hertz or 0.3 hertz. I always pick 0.3. In the manual, they say 1 hertz. But in the old manual, it was below 1 hertz. Anyway, they meant small frequency. And frequency 2, we're gonna take 50 hertz, equivalent to the voltage you have at home. It's around 50 to 60 hertz. If you put the voltage on 50 hertz and you look at the bulb, so you have two observations to do. And the two observations are the following. You're supposed to look at the bulb. So one, look at the bulb to observe the behavior, and two, look at the graph to observe the behavior. Okay, you can see it through the video or through the experiment next week, since you're gonna do the experiment. Dr. Jimmy insisted that I don't offer you virtual experiments, and I agree with this. So that's why I'm gonna give you 1 week off from lab reports, because we want you to be on campus. Okay, this is like an utmost priority for us. So when you look at the bulb at 50 hertz, 50 hertz is so fast, it's like 50 times per second. Your eye is not gonna see any change in the brightness. It's gonna be bright all the time. And the graph is gonna look ohmic or not, I cannot tell you right now. And when you put 1 hertz or 0.3 hertz, 0.3 hertz, it means it's gonna go on and off once every 3 seconds, like 1/3, right? Once every 3 seconds. This is very slow. You can observe it so easily with your eyes. It's gonna go on, then off, very slow, once every 3 seconds. And the graph is gonna look also ohmic or not, straight line passing to the origin or not. This is one of the graphs you're gonna have. Is that ohmic or not? Can you tell? It's not ohmic, obviously. Okay, so this device is not ohmic. This case is not ohmic. Now this case, is it for high frequency or low frequency? I cannot see here what was the frequency. And to be honest, I don't want to tell you, just to keep a small element of surprise. Here, the question is how frequency is going to affect the brightness, the behavior of the bulb. By the way, this is the real experiment. This is my hand. This is the bulb going on. I don't remember which frequency it is, but probably 50 hertz, because I could catch a screenshot when it's on. Because for the other one, the 0.3 hertz, it's going to go on and off. And probably it's difficult to catch a screenshot when it's on. And these are screenshots of the experiment to show you the connections. This is another connection to show you the bulb. These are the series connection. And this is what you're going to see, a straight line passing to the origin for the series connection and so on. Probably I can add the YouTube link on the same slide in case you want to view the experiment later on. I advise you to go over those in the evening of Monday, like next Monday, if we have an experiment on Tuesday morning. Hey, Tuesday, you will not take a lot of time for both experiments, okay? So since we have 2 experiments next Tuesday, we'd rather be ready, lab report, manual, watch the videos, go over the slides a bit, and get ready. You come do the measurements, you can finish the whole thing in 2 hours. Do you think it's fair? Do you think it's doable? And please do not watch the recorded session again, because I think it's very frustrating. We took 50 minutes. Nobody wants to watch 50 minutes unless you were absent, unless you want to check something, unless you were here but you disconnected for a short while. This is only for emergency. But go over the slides and go over the YouTube videos. The YouTube videos are very short, nothing more than 10 minutes and hopefully below 5 or 6 minutes, okay? And they were done short on purpose, because personally, I cannot watch anything beyond 2 minutes, to be honest. And I don't see why you would be able to. I'm gonna stop recording, but I'm staying behind.